I've been over here in the European Space Agency test center in the Netherlands, and it's really impressive what they've got over there. They tried to simulate every kind of environment from liftoff to space. So when they're doing liftoff, for example, I've shown here, there's an acoustic simulator. So this is basically like standing in front of a speaker in oxygen. You've just got this massive speaker here, and it's inside a room, soundproof room, close the doors, they put in their satellite, and they turn up the volume as loud as they can, and they simulate what it's like when you're doing takeoff. You know, it's really loud. And other simulators in NASA here, there's a solar simulator. This is a massive vacuum chamber. They put a satellite into it. They've got huge lamps that simulate what the sun would be like shining on a satellite. They turn it on, and they see how their electronics behave, whether the heat will actually degrade the electronics. They've got vibration simulators as well. This is a shaker, they call it. Stick the satellite on it and just shake it as hard as they can, again, to simulate takeoff. You do computer simulations as well. Okay, this is probably something you'd see on PlayStation at the moment. It's Flight Simulator. But they also do more basic simulations, like here I've got a solar cell, and what they're simulating is the temperature. If the sun is shining on the solar cell and one of them fails, what will that do to the rest of the solar panel? So you've really got to think of everything that could possibly go wrong. So the conclusion, what I've tried to show here is that a lot of the technologies are very basic, but you've just got to test all the way. Okay, I'm going to move on to what I've called space myth number 4, and it's Ireland in space. And I found this on the web there a few days ago, and I suppose it's the impression that people get when they think Ireland in space. No way, these guys are going to mess it up. I mean, you're not going to leave an Irish guy send something up into space. But okay, if you look at on a world scale, yeah, we're very small, and the thing is, there are only 2 countries who are very big, really, at the moment anyway, and that's the USA and Russia. I have a chart here of the number of launches per year that each of the countries have done, and you can see that the United States and Russia, of course, are way ahead of everybody. But Europe have quite a number as well. They've had, between 5 and 10 launches over the last 10 years. Japan and India as well, and of course, sleeping giant China is coming up and overtaking everybody. So we're small on a world scale, but there's a lot going on, and it's mainly driven by the European Space Agency. So probably a lot of people are familiar with the NASA, the North American Space Association, but the European Space Agency has been on the go for kind of since the 50s, really, but it's really come together as an organization in the 70s, and it involves most of at least the early European countries, and there's some associated countries as well, like Switzerland. And they really cover everything that could be covered in space. They do Earth observation, they do extraterrestrial observation, they do all kinds of things really in space, communications. So that should be your first port of call if you are interested in the whole space area. So Ireland's interaction with the Space Agency has been ongoing since about 1975, and we've actually been putting money into the Space Agency every year. It's the last number I could find was 12 million in 2005. That's probably gone up a little recently. So we're actually putting money into the Space Agency every year. The first question you should be asking, okay, what are we getting back? But we are getting money back, and there's a geo-return policy. You just about see it down here. What that means is whatever we put in, we should be entitled to get it back out as well. So we're putting 12 million in, we're entitled to go in and bid for projects, and if you've got a good idea, you can go to the European Space Agency, and hopefully they'll give you a nice wad of cash to carry out your brainwave. So you can see we're doing lots of different things, from basic science to launchers to navigation, so all kinds of different things. And okay, this should be an eye-opener to a lot of people. There's actually an awful lot going along in Ireland, everything from propulsion, so liftoff, to high reliability components, microwave components, that's transmission, optoelectronics, software, and telecommunications. So this is taken from the Enterprise Ireland website. There really are quite a number of companies around Ireland developing technologies, and they're actually up there in space at the moment. So I'm going to try and focus on where I work, and that's what I know best. That's the background that I have, and it's with the Tyndall National Institute in Cork. And we're a research institute. We're focusing on electronics and photonics. That's things to do with light, devices that detect and send out light. And we're a mix of staff and students, so we're associated with a university. But our role with the European Space Agency goes back about 20 years, even back to 1982 actually, and in 1988 we were designated a microelectronics test and support lab. So what that means is ESA say, okay, we've got a rocket, there's something going wrong in it, here's a piece of equipment, can you test it? So we'll take it in, we'll do a little bit of testing, and we put together a report on it. And the kind of things that we do, so there's a nice picture here missing of a thermal shock chamber. We try to simulate, let's say, the heat environment in space, going from hot to cold if you go in front or behind of a planet. Mechanical shock, if something gets dropped, try to simulate what's that like. Again, we have high temperature testing equipment, humidity equipment. So what we would usually do, the types of things we do are long-term storage testing, reverse engineering. So we take a device, basically tear it apart and see how it works. And if something goes wrong, we're trying to find out what goes wrong with it. And if we need more detailed analysis, we use more advanced equipment. We can do X-ray imaging. So if we need to look inside a piece of equipment or a device, we've got this X-ray machine that can look in there. We can do thermal imaging, which basically means if we've got a piece of electronic equipment and it's running too hot, but we don't know where the heat is coming from, you can get this thermal camera that can look inside the device and tell you where the hot spots are. And if we need to do really advanced analysis, we have various what are called electron microscopes. So instead of using light, use electrons to look at very high resolution at materials. These are basically atoms you're looking at here. So you can look down to an atomic level and seeing, okay, are the atoms lining up right or are they failing? So the types of technologies we've developed, the first major technology was a device known as a RadFET. So it's a radiation field effect transistor. So what this does is it detects radiation at very low levels. And it's very sensitive, and it uses very little power. And what this was used for by the European Space Agency, they would put it on their equipment, let's say satellites going up into space, a sensitive piece of equipment, and this will detect how much radiation is coming from the sun, basically, whether it be UV radiation or charged particles. And it will tell you how much radiation your piece of equipment has been exposed to. And then you can work out, okay, this piece of equipment is going to last for a year or 2 years or whatever. So as I say, it's been used by ESA at the moment. It's up there in space. The second general area of equipment we've had out there are what are called millimeter wave devices. So these were initially used for looking out into space and looking at objects that emit very high frequency signals. And these devices can detect the signals and give you an image of what's out there, something you couldn't see otherwise just using the naked eye or optical telescopes. And more they're being used for communications, and even more recently you can use these devices for looking at the atmosphere, let's say around the Earth, for Earth imaging, and I'm going to show you a picture of that later on. This is a project I was directly involved in, and it's called the Bepicolombo mission. The European Space Agency are going to send a satellite to planet Mercury, which is the closest planet to the Sun, in 2014. And they have various reasons for why they want to do it. It's quite an interesting planet. It's so close to the Sun, it gets affected by gravity so strongly, it's got extreme temperatures. But the bottom line is, the temperature is going to be as high as 350 Celsius. The satellite is going to hit that kind of temperature. So you can imagine, you have your mobile phone, and you pop it into what I have here, an oven. An oven only goes to about 275, your kitchen oven. What's going to happen? It's going to melt. So we've got to develop electronics that are going to last up to 350 Celsius. So what we've had to do is, just a bit of background, most electronics out there in your computer, in your mobile phone, your TV screens, they're based on silicon. It's one of the most common materials out there. It's basically sand that's been purified. It's been heat up and purified. But silicon works great up to about 100 degrees Celsius, maybe 150, and then things start to go belly up. It doesn't switch on when it's supposed to switch on, it starts failing, so things go all over the place. So the European Space Agency decided, okay, we've got to consider alternatives here. Chances are silicon is going to fail. So they looked at these new materials, and two in particular, gallium nitride and silicon carbide. Gallium nitride, you might not know it, but I presume everybody has some kind of an LED light, either on their bike or in a torch or whatever. Those LED lights are made from a material known as gallium nitride that was developed about 20 years ago. And in fact, the first gallium nitride Grown in Ireland was here in Trinity about 10 years ago when I started my PhD, just the group I joined. So it's amazing how quickly it's actually been taken up as a space technology. But what it's got is, it's got a much higher melting temperature than silicon. It's got a much higher, what's called a breakdown field. So you can turn up the voltage across this material and it won't break down. You do this with silicon and it'll start leaking current. And it's got a band gap as well, an electronic band gap. And again, that's basically a number that tells you when your device switches on. So these materials are much more promising than silicon. But they're very new, so the space industry is a little bit wary about using them. But we had some experience of developing devices in these materials down in Tyndall. So we have developed this kind of a device. It's called a solar cell protection diode. And what it basically does is, if you've got a large solar panel, and let's say a shadow comes across part of it, some of your solar cells get turned off, basically, and they can go into what's called reverse bias, so they can damage the rest of the panel. So these are little protection devices to protect in case that happens. Let's say if you go behind the moon or something like that, or you get partially shadowed. So we test our devices up to 300, 350, up even to 400 Celsius. And we would test typically for 1,000 hours. So basically you pop these things in an oven for 1,000 hours, you check them every now and then, you come in the morning, you check them. It's like looking after a child sometimes, you just have to keep an eye on them, see where they go wrong. But they behave pretty good. At 400 Celsius, we start to see things going wrong all right. So we're trying to find out why that is. So as I show here, they've done very well, but some of the devices, you're driving these things so hard, you're heating them up to 350 Celsius and you're driving high current through them that the slightest mistake in your process or something is wrong in the device, you get catastrophic failure. The whole thing just burns in a shot. So that's what happened to some of the devices. So that's where the science comes in. You go in and you look at your process and you're trying to find out where these things go wrong and you investigate. So, okay, that's pretty much an overview of what we do at Tyndall and what Ireland is doing. So what I'm going to try and do now is maybe give you an overview of, you've seen what goes on out in space, and I'm sure all of you are asking, and the taxpayer is asking, okay, we're spending so much money on space technology. Is it any good to us? Is it coming back down to earth? And okay, I took a look at the NASA website and the ESA website, and they've got hundreds and hundreds of what they call spin-off technologies, things you never knew came down from space. Scratch-resistant lenses, for example, and self-adjusting sunglasses. And that's all well and good, but is it really worth all the money we're investing in space technology? So I'm going to try and highlight a number of areas where I think there's been significant progress in space technology and how it's been taken back down to Earth. The first one of these is in solar and fuel cells, and I'm going to just focus on solar cells. And I'm going to go through a few more areas as well: transport and medical and security and environmental monitoring. But the first one is solar energy, and what this chart here shows you is it shows the efficiency of solar cells. If you wanted to go out tomorrow and buy a solar cell, there's actually a lot of options out there, what you could buy. And the option comes from the fact that different solar cells have different what are called efficiencies. How much light you put in and how much electricity you get out. Most solar cells, they only convert about 10% of the light that comes in gets converted to electricity. The rest gets wasted in heat, so they actually heat up and they get less efficient. But the most efficient solar cells, these ones up here, they're about at, I think 43% is the record at the moment. They were developed for space. And they're called multi-junction solar cells, and they're really a smart piece of technology. What they do is, if you look at the sun's spectrum, the sun is made up of all different colors of light: red, green, blue. It's got infrared, it's got UV. So it's got all the different components of light. So if you could capture each one of those components, then you'd have a lot more efficient cell. That's the problem with most cells. They only capture one part. They might capture the red part. So what space solar cells do is, they've got different materials, they capture different parts of the solar spectrum, and they're much more efficient in that way. But at the same time, they're very difficult to make. You can imagine trying to put all these materials together and make sure they all give out the right amount of current and that you match everything up is very difficult. So that's a big challenge. but they are being used down on Earth, and they're, as I say, they're the most efficient solar cells you can get on Earth at the moment. And in places like Spain and America, especially in big desert areas, they're using these cells with huge, what are called concentrators. They've got massive lenses or mirrors, and they're focusing down the light, and they're running these things at very high light concentration, a bit like a magnifying glass. And they're very efficient, but as I say, they're very hard to make. And we're working on this area at the moment, down in Tyndall, and we're looking at new materials, gallium nitride, like I said already. We have a reactor, as it's called here. It's a machine that can grow this material, because potentially gallium nitride could be the most efficient solar cell material of all, because it captures all of the solar spectrum in one material system. So I think that's the way it's going to go with solar cells. The next area is space technology for electric cars. Probably in 10 years' time, most of us will be driving an electric car or a hybrid electric car, as they're called, a HEV. So you've got an electric engine and you've got a petrol-driven engine or a fossil fuel-driven engine. But to operate your electric engine, you need high-temperature electronics. If your electronics actually run very high because you're running very high current in your car, to drive the car. So these electronics have actually already been developed for space. So what's happening at the moment is they're taking the technology that's been developed for space, and they're incorporating it into the transport industry. And even at the moment, we're involved in a European project down in Tyndall where they're trying to make an all-electric car based on silicon carbide electronics. Okay, the next area I'm going to look at is space technology for health. And this, you might have remembered, I showed you a device that Tyndall had developed for radiation monitoring in satellites. Well, there's a US company have taken this technology, and they're using it for monitoring radiation dose in cancer treatments. So it's a tiny little device that you can either put on a patch on your face. I actually have it in here if anybody wants to look at it afterwards. And it'll monitor how much radiation you're getting during, if you have to go through radiation treatment for cancer. They can also implant it, this little thing here. You can implant it beside a tumor, or actually in the tumor, if you want to measure how much radiation dose you're getting, because it's critically important. If you get too much radiation, you're going to kill healthy cells around you. If you don't get enough radiation, you won't kill the tumor that's doing you harm. So this is, I think, the world's first implantable wireless radiation detector for medical applications. So there's no wires attached. You just put it in there, you get a little detector, and it tells you how much radiation you've given. So that just came on the market, I think, last year in the US. Some of you are probably familiar with CERN in Switzerland, in French-Swiss border. This is a large synchrotron. Basically, you've got electrons flying around in a circle, and they give off radiation of all different types. And it's a huge scientific facility. It's one of the most advanced in the world. And the RadFET, or the devices that were developed in Tyndall, are being used in CERN at the moment. There's a company in Cork called Smith Detection. They've taken over Farn technology, which came out of Tyndall, and they develop systems where it's for security monitoring in airports, so they can basically see if you're carrying a gun or a knife or whatever, bottle of whiskey. And that, of course, is hugely important now, especially in the US. This technology is also being used for environmental monitoring, so they can basically look down from above with a satellite and tell you how much different pollutants you have in your atmosphere, whether you have nitrous oxide or CO2 or ammonia. And again, if you go to the ESA website, you can look at some amazing images. If you want to see how smoggy Dublin is, you can just click on there. And this was all developed from this, what's called terahertz imaging, so it's very high frequency. Your mobile phone works on gigahertz technology. This is 1,000 times faster. It's terahertz. Okay, the last part. The career options, why you're all here, maybe. Okay, well, what I'll try to do here is briefly give you an overview of what are your options. If you're interested in space and you're interested in doing something that's related to developing space technology, where do you go? And I suppose straight away you might think of, okay, the only option is an astronaut, or I'm going to be some wacky astrophysicist that's going to look at galaxies miles away. But there are a number of options. The first one is to join an international organization like the European Space Agency, NASA, JAXA here is the Japanese Space Agency. There's quite a number of national space agencies around the world. And they do everything, as I say, from looking at the Earth, looking to outer space. They put up satellites for TV. Whatever you're interested in, they cover them. The second option would be to go directly into the space industry. So these are the companies that actually do the work for the international organizations, sending up the satellites. These are huge aerospace companies that would send satellites up into space, and we would have worked with some of these. The third option, nice option, is to work in an observatory, usually in very nice sunny locations because they need as little cloud cover as possible. So you get places like Hawaii and the Canaries that have, or South America, where they're looking up into space from the Earth, and they're looking at what's out there.